Hi everybody, welcome back to the TETRIX RoboBench video series. This is Tim and we are now ready for activity number 9 in our TETRIX PRIZM programming guide. The name of this activity is Drive in a Square. So first two activities with our taskbot, we simply drove forward. On the second we drove in a circle, we added a turn to that. And now we're going to build on those navigational skills that we've been working on by actually programming our robot to drive in a square. Sometimes it's very important to be able to make precise turns. So that's what this one is about. So let's gather our material. We actually need, again, our fully assembled taskbot, prism mounted on top, fully charged battery, and we need to have our USB cable to be able to make the two talk together. So let's start by going ahead and let's open our sketch. If you have any other open sketches that you've got that you want to save, make sure you do that now. But in our Arduino software, if we go up to the File option, go to Examples, down to the TETRIX PRIZM, and we are ready for TaskBot Activity 9, Drive Square 1. That's the one that we want to open up. So as soon as this opens up, we're going to expand our window here so that we can see everything. This is a little bit more of an intimidating type of window because actually we're seeing quite a bit of code here. But actually, don't be intimidated by that because it's a little bit deceptive. It's all sequential. It's just that there's more commands than what we're used to. When we take a minute to read our comments, we'll see that the program is intended to make the taskbot drive in an actual square. So let's go ahead and upload this. Let's make sure we make our connections from our taskbot to our computer. Just like this right here. Let's go ahead and power on our taskbot. Check for our lights that tell us everything is right. We've got a blue power light, green light over here. We're ready to go there. Go into our software to verify our code. It looks like it's actually verified everything is right. Now we can go to upload. Click on my upload button. Verify that I have data transmitting. As soon as I get the message that that's all done, verify my green light, power light, I'm ready to go. Like our other examples with the taskbot, we don't have enough room to do this on the tabletop, so I need to disconnect. Actually set my robot down on the floor and actually execute the bot. So let's do that right now. So now that we've seen our robot perform, let's actually talk a little bit about what we actually observed as far as the behavior. Chances are very good that the robot didn't actually drive a true square. It might have made 4 turns, it might have made 4 forward behaviors, but they probably didn't come together to make a perfect square. And there's probably very good reasons for that. Depending on the type of surface that it was on, and the friction coefficient between the wheels and that surface, the robot either probably overturned or underturned. So what we need to understand is that depending on the surface that you're on and the power level that you have for your battery, and because we're using time as the duration or the determining factor on how long our robot will turn, we will probably need to go in and adjust that duration or that time factor so that we can actually make the 90-degree turn for the specific surface that our robot is traveling on. So you'll probably want to go back and do that. But let's go ahead and talk a little bit more about our program because it was pretty intimidating because of the long amount of code that we saw. If you look down through there, we haven't used anything different. We've used a lot of the same commands that we've already experienced with the other programs. We just actually made a longer list of those. And when we've done that, we've created a very specific behavior. But one of the things that we are doing with this and it's important for us to recognize is that when we're navigating like this, we're using the delays, the times, to actually determine how far the robot either moves forward or it turns. And this kind of a process, using time as the determining factor or the parameter that defines the movement, is called dead reckoning. And an important thing to remember about that in this type of an application is that that time factor is very much impacted by a couple of things. And one of the main things is the power level of our battery. So if we have our power level at full charge and it's sending full power to our wheels, and we have, again, the similar time factor involved, we discovered in our first TaskBot activity that that speed, that power level, impacts distance traveled. So when you think about that in this particular activity, you can see that if your power level is a little bit less because you've made several runs and your battery level has gotten lower, it can impact how far the wheels travel in that same time frame. So that's an important thing to remember, that when you're trying to use time as a determining factor for how far a wheel travels or your robot travels, that battery charge can cause some variance from time to time. So that's an important thing to remember. But this is a basic behavior that it's important to understand, because you're not always going to be able to go in a circle. You're not always going to be able to go straight forward. It's important to be able to make precise turns. So that's where this actually exercise really becomes an important beneficial activity to understand and see how it works. We can play with the code and actually change some of those variables and see if we can create how it impacts the variable, the actual behavior of the robot when it's attempting to drive that square, and I encourage you to do that. We talked about dead reckoning, and more is kind of explained with that if you actually have access to the programming guide. I would encourage you to look at the comments that we have in the programming guide to get a little bit more deeper understanding of how that dead reckoning is determined. But let's talk about a little bit about real-world connections. In our real world, sometimes there are special vehicles in like a factory setting that have to travel a similar path time after again. And this is kind of something what we've done here is we've created a static path that basically should be the same. So that's kind of an example of how a real world a vehicle might have to do this similar behavior. STEM extensions, obviously from the science standpoint, we've got a relationship between time, distance, and velocity. Technology, how much time is used when you are working with a microprocessor, how does that actually interact? Obviously measuring the turning radius. Engineering, actually, we could talk about the program design for following a specific path. Math, we could talk about relationships of sides, angles of the square, actual measurements of an angle. So there's lots of those STEM type extensions that we could actually use this behavior to talk about. But let's take it one step forward then with our hacking the code activity. Where are you going to move this from here? And this is where there's a lot of actually options available to you. You could try and create a program that is exactly what we've done, recreate that on your own to get a little better grasp of the syntax structure of a sketch, or you can change that if you're a little bit ready for something else. How about defining something other than a square in a geometric pattern? How about an octagon or something like that? Or maybe something a little bit more challenging. How about a letter of the alphabet? There's several things that you could do to actually create a specific path that your robot has to follow. So I would encourage you to try and do something like that. So hope you found that informational, inspirational, and like we always say, have fun, build some robots, come back and see us.